In this course, we will focus on understanding battery specifications, which are essential for evaluating performance, reliability, and safety. We will discuss key parameters such as capacity, voltage, temperature effects, depth of discharge, C-rate, safety mechanisms, and degradation processes. By the end of this session, you will understand not only how these specifications are defined, but also why they are critical in selecting the right battery for different applications, from cars and renewable energy systems to portable electronics. Battery specifications are the foundation for evaluating how well a battery will perform, how reliable it will be, and whether it is suitable for a given application. The most important parameters include capacity, voltage, temperature effects, depth of discharge, and the C-rate. By understanding these values, engineers and users can select the right battery for their needs, whether that is starting a car, storing renewable energy, or providing backup power in critical systems. In short, battery specifications guide both performance expectations and long-term reliability. Battery capacity is one of the most fundamental parameters. It defines the total amount of energy a battery can deliver. We usually describe it in ampere hours, or R. For example, a 100 Ah battery can deliver 5 amps for 20 hours. We also use reserve capacity, which measures how long a battery can supply 25 amps before the voltage drops to a critical level. Cold cranking amps, or CCA, indicate how well a battery performs at low temperatures, especially important in automotive applications. Voltage is another essential parameter. A single lead-acid cell has a nominal voltage of about 2 volts. That means a 12-volt battery contains 6 cells connected in series. Open circuit voltage indicates the state of charge, while charging voltage increases when current flows. By connecting batteries in series, we increase the total voltage. In contrast, parallel connections increase the available current while keeping the voltage constant. This is crucial when designing systems like renewable energy storage or UPS applications. Modern batteries, especially lithium-ion, require advanced safety systems. A battery management system constantly monitors voltage, temperature, and current at the cell level. It prevents hazards such as overcharging, deep discharging, or thermal runaway. Safety features include thermal fuses, cooling systems, current interrupt devices, and robust casings. Together, these mechanisms ensure that batteries operate efficiently and safely, even under demanding conditions. Temperature significantly impacts both lead-acid and lithium-ion batteries. In cold conditions, batteries experience increased internal resistance, which directly affects their power delivery. For lead-acid batteries, this also brings the risk of electrolyte freezing, especially if the battery is not fully charged. On the other hand, high temperatures accelerate chemical reactions, leading to faster degradation and increased self-discharge in lead-acid batteries. Lithium-ion batteries also suffer at both extremes. Low temperatures can cause substantial capacity loss and safety concerns, including the formation of lithium plating, which can lead to dangerous thermal runaway. Electrolyte freezing is also a risk for discharged lead-acid batteries. At high temperatures, chemical reactions accelerate, leading to faster degradation, capacity loss, and active lithium loss in lithium-ion cells. Both extremes increase the risk of thermal runaway. This is why thermal management systems, such as air or liquid cooling, are essential to maintain safe operation. Battery safety mechanisms work at 3 main levels. Thermal safety mechanisms prevent overheating and thermal runaway. Active cooling systems and thermal fuses protect the cells, while gas sensors detect hydrogen, carbon monoxide, and carbon dioxide as early warning signs of dangerous reactions. Electrical safety focuses on keeping the battery within safe operating limits. Overcharge and over-discharge protection prevent stress on cells, balancing systems keep voltages equal, and current interrupt devices stop excessive current flow before it causes damage. Mechanical safety provides physical protection. Strong casing designs protect against external damage, and integrated fire detection and emergency shutdown systems add another critical layer of safety in case of severe incidents. Battery degradation is caused by multiple interacting factors. These include high C-rates, poor thermal management, material quality, and cycling depth. In lithium-ion batteries, the most common degradation mechanisms are say layer formation, lithium plating on the anode, loss of active material, electrolyte decomposition, and mechanical stress due to volume changes. These processes reduce efficiency, cause capacity fade, and increase safety risks. Understanding these mechanisms is key to designing strategies for longer battery life. To summarize, battery specifications provide the foundation for understanding performance, safety, and longevity. We have seen that parameters such as capacity, voltage, temperature effects, depth of discharge, and C-rate directly affect battery life. Safety is ensured by advanced protective mechanisms and thermal management systems. Finally, degradation is an unavoidable but manageable process if batteries are operated within safe limits. By carefully balancing these factors, we can maximize efficiency, safety, and durability across different battery applications. Thank you for your attention. Batteries are not only at the core of today's technologies but also central to a sustainable future.